In this presentation, we will provide information about overall the concept of OEE, overall equipment effectiveness is, and how it plays a critical role in lean manufacturing. By explaining the three key components of OEE and the calculation method, we will discuss how to calculate it through practical examples. We will also focus on OEE scores and the advantages of it and discuss the impact of the 6 big losses on OEE. By providing examples based on types of losses, we will see how to effectively use the OEE tracking system and analysis tool. OEE, overall equipment effectiveness, is an important productivity indicator that shows how close an equipment is to its true potential. Its main purpose is to identify opportunities for improvement by making loss areas visible. This way, businesses can clearly see which aspects of the production process need to be improved. OEE, a concrete example of the principle you can't improve what you can't measure, should be properly monitored and analyzed for sustainable production success. OEE directly contributes to eliminating waste in lean manufacturing. By making losses in the production process visible, it reveals improvement opportunities. It plays an important role as a guiding benchmark for real-time decision-making in Gemba, the production site. This allows teams to make more informed and effective decisions. In addition, by setting team-based targets, it encourages operators to actively participate in the process. Daily OEE targets motivate team members and contribute to overall performance improvement. OEE consists of 3 key components: availability, performance, and quality. Availability refers to the actual working time of the equipment within the planned time. A machine that stops due to malfunctions, adjustment time, or die changes reduces this rate. For example, if a shift is scheduled for 8 hours of production, but there is 1 hour of breakdown and 30 minutes of die change, availability significantly decreases. Performance measures the operating speed of the machine. If a machine theoretically produces 60 units per minute but only outputs 300 units per hour, there is a speed loss. Micro-stops, slow operation, or operator-related delays are the main causes of these losses. They are usually hard to notice, but OEE clearly reveals this drop. Quality shows how many of the produced products are defect-free. For instance, if 5 out of 100 units are defective, the quality rate is 95%. Defective production causes not only time but also cost losses. OEE combines these 3 components to measure the actual efficiency of the equipment holistically. Availability shows how much of the planned time for production of a machine was actually spent operating. This rate is directly affected by stoppages such as malfunctions, adjustment, die changes, and operator delays. Therefore, it is vital to correctly classify and code the reasons for stoppage. Short stoppages are often overlooked, but they can have significant impacts on overall effectiveness. For this reason, every stoppage should be recorded with its duration and reason, and monitored regularly through stoppage analysis boards. The calculation used is quite clear. Availability equals planned duration minus downtime, divided by planned duration. This formula provides a strong guide for continuous improvement by showing how much machines contribute to production. Performance expresses a machine's ability to produce at its ideal production speed during non-stop operation. This rate can be negatively affected by factors such as operator slowness, inadequate settings, or old equipment. Short stoppages also cause significant performance losses. Therefore, continuous analysis should be done using tachometers, counters, and timer systems, and standard cycle times must be clearly defined. Because these times answer the question, how much should this machine actually produce? The formula used in performance measurement is as follows: performance equals total production multiplied by the standard cycle time, divided by the actual operating time. This calculation provides a strong foundation for improvement by revealing speed losses with concrete data. Quality refers to the proportion of defect-free and intact products within the total production. A low quality rate leads to problems such as rework, wastage, or customer complaints, increasing dissatisfaction. Therefore, it is very important to establish quality control points in the production line and monitor them regularly. In addition, wastage reasons must be analyzed and defined in production-based catalogs. Calculating quality is quite simple. Quality equals intact production quantity divided by total production quantity. This ratio clearly shows how efficiently and defect-free the production process was executed and provides guidance for improvement steps related to quality. Our planned time was 480 minutes, but the machine only operated for 420 minutes. That means there were 60 minutes of downtime. These downtimes reduce availability. A total of 800 units were produced, but 40 were defective. So, there are 760 intact products. This affects the quality rate. Each part has a target cycle time of 30 seconds, meaning the machine should produce 2 parts per minute. We can use this data to calculate the performance rate. First, let's calculate our availability rate. The planned time was 480 minutes, but the machine only operated for 420 minutes. This shows a downtime of 60 minutes. This downtime reduces the availability rate. The calculation is scheduled time minus downtime, divided by planned time. For example, 480 minus 60, divided by 480, equals 87.5%. So, our machine operated 87.5% of the planned time. Now let's look at the performance rate. The target cycle time is 30 seconds, meaning 2 units per minute. A total of 800 units were produced, but 40 were defective. So, there are 760 intact products. To calculate performance, we multiply the production quantity by the standard cycle time and divide it by the actual operating time, production quantity multiplied by the standard cycle time, divided by the actual operating time. For example, 800 times 30, divided by 420 times 60, equals 95.2%. This shows that our machine operated very close to the target speed. Finally, let's calculate the quality rate. Out of 800 units produced, 40 were defective, which means the intact product rate is 95%, intact products divided by total production. For example, 800 minus 40, divided by 800, equals 95%. Multiplying all these rates gives us the overall equipment effectiveness, OEE. OEE equals availability times performance times quality. That is, 0.875 multiplied by 0.952, multiplied by 0.95, equals 79.1%. Specific scores are used to interpret OEE, and these ranges clearly show the status of our production efficiency. OEE of 85% and above represents world-class production and indicates that machine efficiency is very high, providing a world-class production process. OEE between 70% and 85% is a good level but still indicates that there is room for improvement. OEE between 50% and 70% suggests there are critical areas with significant losses and inefficiencies that need to be improved. An OEE below 50% is an alarming level and indicates serious problems, urgent action is needed. These ranges help evaluate our production processes and make improvements. A high OEE means the production process is efficient and effective, while a low OEE indicates areas that need improvement. OEE provides great advantages for improving production processes. First, it enables data-driven decision-making, allowing for more reliable management. It also sets goals for improvement projects and measures machine efficiency, showing which machines are operating more efficiently. It increases operator awareness and promotes a sense of ownership over their machines. It guides lean transformation processes and makes lost times visible, which creates continuous improvement opportunities. OEE is an effective tool for increasing production efficiency. There are various losses that affect efficiency in production processes. The first of these is malfunction losses, which occur due to unplanned stoppages such as machine breakdowns or power outages. Adjustment and adjustment change losses include planned but efficiency-reducing activities such as die changes and product transitions. Another significant loss type is idle operation and waiting, which includes operator waitings or faults in material supply. In addition, short stoppages, speed loss, and quality losses can also negatively impact the production process. Managing these losses is critically important for more efficient production. There are several important factors affecting machine availability. Machine malfunctions are one of them. Mechanical, electrical, or pneumatic problems can cause interruptions in production processes. In addition, prolonged durations of scheduled maintenance are another factor. Failure to fully comply with maintenance procedures can cause these processes to take longer and result in production losses. Material waiting issues can negatively affect the production flow due to internal logistics problems or material not arriving on time. These factors directly impact machine efficiency and must be carefully managed in the production process. There are several important factors that affect performance. Slow-running machines cause production to fall below the target speed, negatively impacting efficiency. Failing to produce in accordance with standard cycle time also leads to losses. For example, if the target cycle time is 30 seconds but the actual cycle time is to 40 seconds, this decreases production efficiency. Operator interferences can cause time losses. Continuous adjustments, speed changes, or hesitation before stoppage can negatively affect production speed. There are several important factors that affect quality. The number of defective products after production encompasses items that are returned or cause customer complaints. This must be monitored carefully, because poor quality products negatively affect customer satisfaction. Reworked products are corrections made after production is completed. This results in additional labor and time loss. Importantly, it may increase our costs. Errors caused by the operator occur as a result of non-compliance with instructions, lack of knowledge, or carelessness. Material-related quality problems are also quite significant. Defective raw materials or unsuitable semi-finished products from the supply can cause serious losses. Finally, inadequate process controls can lead to a lack of checkpoints and late detection of errors. By paying attention to these factors, it would be possible to improve. When setting up an OEE tracking system, identifying the machines is the first step. Critical machines, bottlenecks, or high-capacity machines should be prioritized. In the second step, data collection methods are selected. At this stage, manual forms or sensor-assisted systems can be used. In the third step, standard cycle times are defined. Defining separate cycle times for each product and machine is critically important for accurate future analysis. These steps are the cornerstones for the successful operation of the OEE system, and each directly affects process. We will examine some important tools used in OEE analysis. Pareto analysis helps us identify the most common types of stoppages or errors. In this way, we can solve problems more effectively by targeting major losses. The Ishikawa diagram is used to analyze the root causes of low OEE. By categorizing into human, machine, management, and material, we can identify areas that need improvement. The 5 whys analysis allows us to ask the question why at least 5 times to get to the root of each problem, so that we can conduct an in-depth analysis. Gemba walks allow us to recognize hidden losses and problems through on-site observations. These tools, when used together, make our OEE analyses more effective. Transparent data usage plays an important role in improving the motivation of teams and fostering a culture of continuous improvement. With daily and weekly graphs, shift-based changes and team performances can be tracked, which enables important support in teams reaching their goals. Operators help speed up the process by quickly reporting downtime or quality problems. Using color codes is very useful in this process. Green indicates that the target has been achieved, yellow indicates a critical level, and red indicates a situation that requires immediate intervention. These visual indicators enable teams to quickly recognize problems and take action. In addition, OE-related downtimes and shift targets are displayed on large screens in the field, providing instant information flow. This transparency increases team motivation and facilitates performance tracking. Teams put in more effort to improve their performance as they see real-time data. OEE is like a health report of our production processes. Improvements can only be made with accurate measurements. Therefore, continuously tracking OEE is a critical step to improve our processes. OEE is the intersection point of lean and digital processes. By systematically monitoring each component, we can increase our production efficiency. Effective use of OEE establishes the strong link between visibility, awareness, and action. In this context, OEE is not only a measurement tool, but also a matter of culture and discipline. Accurately tracking OEE is the key to achieving continuous improvement in production processes. Thank you for attending our training. If you have any questions, please